Hi, Dr. Nixon. How are you?
Hello, Year 8. And today I am doing an experiment.
Yeah, and it's got red food colouring, washing up liquid, vinegar and baking soda.
Excellent. So we have a small bottle here, and the first thing I'm going to do is I'm going to add
Baking soda.
a rounded tablespoon of baking soda.
You call it
Peter,
soda.
are you there with your rodder? This thing. There you go. Help me get that in. Yeah, jam that down. Cool.
Dad,
There we go.
Dad, when are we going to put the red food dye in?
In a sec.
Okay.
You have to call him Dr. Nixon when you're in a lesson.
But we're his children.
Nearly there. I'll shorten this on you. Cool. Next, we're going to add a little bit of a squirt of washing up liquid. Yep. That'll do there. Probably. That was almost a bang head situation, wasn't it? Where are my lab specs, guys? And where's our PPE?
It's okay. It's a kitchen chemistry.
Kitchen chemistry. All right. I'm going to do this because I don't want you getting this all over you. No. So a little bit of red. Oh, okay. Well, there we go. That was quite a lot of red food colouring. And I'm going to pour in some vinegar. Right. Which one of you is going to pour in the vinegar and which one of you is going to hold the funnel?
I'll hold no, can you hold the funnel, Dad?
It's alright, I'll let you two do it. Charlotte, you're going to pour. Right, Charlotte, you just, as soon as Peter's poured that in, which he's going to do quickly, remove the funnel. Quick. Yeah, there we go. And lift. Up.
Lift.
There we go. Explosion.
Oh my gosh!
Run! What do you think of that?
Get your hand out the way, Charlotte.
Is that the best one we've done so far?
Yeah.
Do you like the red colour?
Yeah.
Does it stink? Say goodbye, Year 8.
Bye, Year 8. It's a whip.
So, hello Year 8 and welcome back after your Easter holidays. I hope you managed to have a good rest and that you're ready for more learning. What was the point of that, you might ask? Well, normally when I do this lesson, the wonderful Mr. Reeves comes in with his scaled up version of Mount Tambora or Mount Krakatoa or something like that and produces a rather spectacular explosion. Unfortunately, without the wonderful Mr. Reeves, I had to do that in my own kitchen. But volcano explosions, I hope at some stage in the past, maybe at primary school, you've got the chance to do that kind of chemical reaction. Today we're going to be looking at our second type of rocks, igneous rocks here. So igneous, and we're going to be seeing how they're formed, what have they got to do with volcanoes. So looking back to your table, both basalt and granite are igneous rocks. What properties do they have in common? Pause the video and have a think. Right, before I answer that, we need to go back and have a think about the structure of the Earth. And hopefully in your books, you've got a picture of the Earth that looks a little bit like this. And what we're particularly interested in today is this thin layer of solid rock around the outside called the crust and the mantle underneath. So this area here, which is mostly solid rock, but that flows. It's hot enough that the rock is melting and can flow, a bit like plasticine. And what has this got to do with anything? Well, you might remember that the surface of the Earth, the crust, is actually broken up into different things called tectonic plates. And these plates here, you can see the edge of the plates. So you can see the big Pacific plate here. This is all a solid lump of rock, but it is moving relative to the other plates. And of course, you might recognise California down here and know all about the earthquakes they have. Where there are the joins between these plates, that leads to certain interesting natural phenomena. Just a reminder, you do have to have some familiarity with how do we know that actually there are these tectonic plates and that they're constantly moving. Well, the first thing and the most obvious thing is that all of the different continents that we have at the moment fit together like a jigsaw. So these are the modern shapes of the continents, and you can see down here just how well the right hand side of South America matches with the left hand side of Africa, and you can actually start to piece all these bits together like a jigsaw puzzle, and that would be very strange if those two things were not joined, if they had such a similar shape. Other things, and we have mentioned this before, is where you find particular dinosaurs. So this particular dinosaur here is only found in a band in South America and a particular band in West Africa. And again, there's absolutely no chance this particular dinosaur this animal managed to swim across the Atlantic Ocean. So that strongly suggests that these two bits of land at one stage were joined together. And finally, when we look at the rock layers, you saw in the previous lesson on sedimentary rocks how we can have distinct layers. Well, you get areas in South America where the pattern and the size of the rock layers match exactly the pattern and size of the rock layers in South Africa. And again, that's not going to happen by chance. That actually suggests that they were at one part the same continent. As we've said, all of these plates are moving apart. In some places they're sliding relative to each other. So the area in Western America, around San Francisco, California, the plates are sliding side by side. In some places the plates are moving apart, and in other places, particularly here, this plate coming up and smashing into the Eurasian plate. That's why we have such high mountains. That's why we have such high mountains around here, because the two plates getting banged together are causing the mountains to go up, and in fact the Himalayas are growing. Around these plates, around the edges where plates meet, you get volcanic activity, and one of the most famous is this ring of fire. So going from Japan here, down the west coast of America, New Zealand, the west coast of South America, this is called the Ring of Fire. It's an area of frequent earthquakes and where there are loads of volcanic eruptions, loads of volcanoes, 452 volcanoes to be precise. And here's a fact to scare you: over 50% of the world's active and dormant volcanoes, 90% of the world's earthquakes and 81% of the world's largest earthquakes occur in this Ring of Fire. Very fertile land, but definitely somewhere that you want to be a bit aware of your natural phenomena. So what is a volcano? Well, basically a volcano is like a safety vent in the earth. Down here in the mantle, we've got very hot molten rock under quite high pressure, and it wants out. And wherever there's a weak point in the Earth's surface, which is usually where two plates meet, this hot molten rock under pressure can force its way out onto the surface. Gases and rock, when pressure builds up here, so when pressure builds up, eruptions occur. This is the safety vent opening. Gases and rock shoot up all through the opening, spilling lava, gases into the atmosphere and down the sides. As it says down the bottom, there's loads of different things that eruptions can cause. If you're near them, it can cause mudslides, avalanches, ash and floods. They can knock down entire forests, can trigger tsunamis. That is huge waves in the ocean heading towards land. Flash floods, earthquakes, mud flows and rock falls. Living near a volcano, an active volcano, is dangerous, but the advantages are you often get very fertile soil. Did you know the word volcano actually comes from the little island of Volcano in the Mediterranean Sea off Sicily? Centuries ago, this is quite a nice idea, people living in this area believed that Volcano was the chimney of the forge of Vulcan. So Vulcan was the blacksmith of the Roman gods. So just like your blacksmiths would have worked in very hot conditions, very hot furnaces to make horseshoes and other ironmongery, they believed that the god blacksmith was called Vulcan, and they thought that Volcano was his chimney. And so as he made these thunderbolts for Jupiter, who was king of the gods, and weapons for Mars, the god of war, as he was making these, as he was hammering the metal into shape, this would cause the volcanic eruptions. I'd like you now to just sketch this in your books. See if you can match the keywords at the bottom to the particular bits of the volcano, and then when you've had a go, restart the video. Okay, well, let's see. Did you get it right? First, down here, this is the crust. This is the surface of the earth, the solid bit. And down below the crust, in the mantle, and creeping up into the crust, you've got magma. This is hot, molten rock. When this magma makes its way out of the volcano and onto the surface, it becomes lava. So lava and magma are the same stuff. It's just magma's when it's below ground, lava's when it's above ground. The chimney through which the magma pushes up is called the vent. Now, what we're going to get onto in the second half of the lesson is that as this lava cools and solidifies and becomes solid rock, that becomes our second type of rock, which is igneous rock. And you can see lots of different layers here of igneous rock, each one of these probably being a different eruption of the volcano. Finally, down at the bottom, we've got the magma chamber, and sometimes if the main vent gets blocked or if there's a weakness, the lava can the magma I should say, can start pushing out through another crack, and it can create a side vent. Hopefully you got most of those right. This is reminding you, or going back and reminding you of the dangers of living near volcanoes, as well as the danger from the hot lava. You can also have tsunamis, floods, earthquakes, mud flows, rock falls. Quite a dangerous scenario. And one of the most famous volcanoes, of course, was Vesuvius near the city of Pompeii. And on 79 AD, it literally blew its top. Tons of molten ash and sulfuric acid gas, sulfur dioxide being pumped miles into the atmosphere. What actually killed people were these things called pyroclastic flows, which were not the lava but gas flows, gas and ash moving at 200 miles an hour, coming up to the speed of sound down the mountainside and just literally engulfing people where they were. And you can see here, these are all the bodies that have been discovered, preserved, people literally dropping where they were hit by the pyroclastic flows. You can see a dog here preserved for thousands of years, killed by the pyroclastic flows and then buried by the ash on top. Not the lava, which is why it didn't burn up, but the ash. And they remained buried for almost 2,000 years, 1,700 years, until 1748, and they started to exhume, if that's the right word, the city of Pompeii and the bodies. to see what a Roman city was like, frozen in time almost. Final thing on volcanoes is that there are two different types of lava that you can get. You can either have acidic magma, so this is magma that has an acidic composition. Now these are sticky and viscous lava. Think of thick honey. So as it comes out of the top of the volcano, it doesn't get very far. It flows really slowly and then it solidifies. And so these types of volcanoes tend to be the sort of volcano you would draw, which are these real high cone-shaped volcanoes. And that's because the lava doesn't get very far before it thickens, solidifies and sets. In contrast, if you've got a kind of magma that's alkaline, this is far more runny, so more like water or oil, and it can run for miles and miles. So as it's thrown out of the volcano, it can run for miles and miles and miles before it sets, and therefore you get much flatter volcanoes. In fact, you might not even notice that they're a volcano if there's not lava coming out of them, because they're much flatter. So here's a thing to think about. What does the eruption of Mount Tambora in 1815 have to do with the song White Christmas? Have a pause, have a think. Well, if you got this, very, very well done. Mount Tambora was about the biggest eruption in recent memory, in living recorded history. There was a louder one, Krakatoa, in 1883, but the biggest one was Mount Tambora in 1815. And Mount Tambora put so much stuff into the atmosphere, so much dust and ash, that 1816, the year later, was known as the year without summer. So the sun couldn't get through the dust and the ash. And as a result, there was something called the mini ice age, or the little ice age. And this was where global temperatures dropped for about 10 years. And this meant that during the winters, then there were sort of lots of snowfall, very, very snowy winters. And there was a very famous writer who was born in 1812, and during his formative years when he was young, every winter, every Christmas would have been snowy, and that was Charles Dickens here. And Charles Dickens was growing up during this mini ice age. Of course, when he grew up and started writing very famous stories like A Christmas Carol, a lot of them were set around Christmas, and in those Christmas times it was always snowing, it was always snow on the ground. And this caused a Victorian resurgence in the idea of a white Christmas, which has persisted to this day. They're actually quite rare, but a mini white Christmas there, we tend to think of that as being a norm. So back to igneous rocks. Did you get this right? So looking at the basalt and granite from your table, we can see they're non-porous, they're hard, they have interlocking grains, and they don't react with acid. So they have interlocking grains, they are hard to use for things like work surfaces, they don't let water through, they're non-porous, they're not permeable, but they have random grains, lots of different sized grains within them. So our second type of rock, igneous rock, is coming from the Latin for fire, coming out of volcanoes. So a reminder that the liquid rock is called magma. When it solidifies, it forms igneous rock. So this is magma, well actually lava because it's above ground, solidifying and becoming rock. So what's the difference between granite and basalt there? Well, the difference is that you can actually see the different grains in granite. You've got very big grains, whereas in basalt you can't see the different grains. Granite has very large grains, basalt has very small grains. Well, why might that be? Why do they have different sized grains? At this point I would normally get the class to do a practical. So they get a chemical called Salol, and they have 2 microscope slides. One of them is being in the freezer, it is very cold. One of them is warm, it's been in a nice oven, so it's hot. The Salol would be kept in a water bath, and you put a few drops of Salol onto your cold slide, a few drops of Salol onto your hot slide, and you leave them for a few minutes, and then you investigate them under the microscope. And what we can see here, this is what you would see if it cooled fast, it would look a bit like this. If it cooled slowly, it would look a bit like this. And hopefully you are convinced and you can see that slow cooling leads to bigger crystals. And you have encountered this idea before when you were making crystals back in the acids topic and you were making salts. Those people who really heated up their evaporating basin ended up with very, very small powders in their dishes, while those people who cooled it slowly, maybe even they didn't have time to heat the liquid, would have ended up with much larger crystals. Another example would be ice cream. If you get ice cream from the supermarket, oh, it's lovely and creamy and delicious. It's been cooled very fast using something like liquid nitrogen. If, however, you let your ice cream melt and then you stick it back in the freezer, next time you pull out, you'll probably find it's a little bit gritty and crunchy. And that's because your ice cream has cooled back down slowly. It's re-solidified. It's frozen in the freezer, but slowly. And so you end up with lots of nasty little ice crystals in your ice cream. You may eat it. You probably will eat it, but it's not as nice as it was when it first came out of the supermarket. So, the size of the crystals is all about cooling. There's 2 types of rock. There's the magma that manages to push its way out and becomes lava. Actually, on the surface, it's going to cool very, very quickly. So this is going to have quick cooling, and so it's going to have small grains. However, if it pushes its way into cracks in the crust, so this is the crust here, it's going to cool much more slowly, and therefore it's going to have large grains. We call the rock that's made on the surface of the earth extrusively, like the exterior, outside. We call the rock that forms inside intrusive, like interior. So having a look here, you can hopefully see that the small grains and the quick cooling is this one. So this is extrusive. Whereas this one has large grains because it cooled slowly. This is intrusive. So you can begin to see that. Right, let's see if you've got the hang of this. On the left we've got gabbro. On the right we've got basalt. These are both igneous rock. Tell me which one is extrusive, which one is intrusive. Okay, well, hopefully you realise that this one on the left, gabbro, has large grains. It has large grains because it cooled slowly, and therefore it cooled inside the earth. It is intrusive. Whereas basalt, as we've seen, has small grains because it cooled fast, and therefore it is extrusive. Not all intrusive rocks have such large grains. It's all about the rate of cooling. Occasionally, if you've got the crust made up of different layers and there are gaps between the layers that are easy to fill, then as the magma pushes up, it might find one of these gaps and quickly flow along the gap between the two layers. And if it does this, it's got a very large surface area. So it's going to cool quickly. And these are called sills when you get a rock running, or the magma running between different layers and forming a big flat area of igneous rock. So this shows different things going on here. The diagram shows different ways in which magma can be intruded. So this is all intrusive rock. And you can see that you can form sills. The bits where it forces its way up are called dikes. And if you've got a large lump, like down here, that solidifies as a very, very large lump, that's going to be called a pluton. When magma is forced into existing rocks, it is much hotter than the rocks surrounding it. Energy is transferred to the surrounding rocks and the magma cools down. The sheets of magma have a much bigger surface area compared to their volume than plutons, so thin sheets cool down much faster. So in other words, plutons will cool the slowest, so they're going to have the largest grains. Then you've got sills and dikes, which cool faster. And finally, you've got extrusive rocks, which cool the quickest and have the smallest grains. So feel free to have a think about these questions. It's not important that you do these in your books, but just have a think about the answers. If you're not sure, by all means, email me. So, as before, there's going to be a question sheet for you to look at. Just work your way through, no need to print it out. Have a look at the questions, see if you can work out what the answers are, and then fill in the quiz online with the appropriate multiple choice answer. It will self-mark. I will hopefully, if you can, try and do this by Sunday so that on Monday I can look at where maybe you had problems and might be able to respond. Next week we're going to look at our final type of rock, which are metamorphic rocks, and we're going to look at the rock cycle. Have a good week until then. Email me if there's any problems. I'll give you my email address again. It's a.nixon@ulstergs.com. Don't message me or show my homework. I rarely notice it, so much better to get me that way. Thank you. Bye bye.